eyes now and let yourself settle into this quiet moment. Take a deep breath in, filling your lungs gently, slowly, feeling the air expand within you like a soft wave rising. Now exhale gently, slowly, releasing any tension as the breath flows out, carrying away the day's weight. Breathe in again, gently, slowly, drawing in calm and peace. And breathe out, letting go even more, sinking deeper into relaxation. Allow your body to feel heavy against whatever supports you, whether it's a bed or a chair, as if gravity is pulling you gently, slowly into a state of complete ease. Imagine now that you're floating in the vastness of space, surrounded by stars that twinkle like distant whispers. In this cosmic sea, there are mysteries that draw everything toward them. Black holes, those enigmatic regions where gravity holds such power that nothing, not even light, can escape. Picture a black hole as a silent guardian of the universe, a point where the fabric of space-time curves inward, inviting curiosity and wonder. According to the latest insights from NASA and ESA in 2025, black holes form from the remnants of massive stars, collapsing under their own immense pull, creating a boundary known as the event horizon. But tonight, we'll explore them gently, slowly, letting their secrets unfold like a dream, pulling you gently, slowly into deeper sleep. As we begin this journey, let's prepare your body for rest. Start with your head, feeling the top of your scalp relax, the muscles there softening gently. Slowly, let any thoughts drift away as your forehead smooths out, releasing the creases from the day. Your eyebrows relax, your eyelids grow heavy, closing gently, slowly over your eyes, which now rest in peaceful darkness. Feel your cheeks soften, your jaw unclench, allowing your mouth to part slightly if it wishes, breathing easily. Move down to your neck, letting it loosen gently, slowly as if supported by invisible hands. Your shoulders drop, releasing the burdens they've carried, sinking gently, slowly into comfort. Feel your arms grow heavy, from your upper arms down to your elbows, your forearms, and into your wrists. Your hands relax, fingers uncurling gently, slowly, palms open and at ease. Now focus on your chest, where your breath rises and falls in a steady rhythm. Let your ribcage expand and contract gently, slowly, with each inhale and exhale. Your back relaxes against the surface beneath you, every vertebra aligning in tranquility. Move to your abdomen, feeling it soften, the muscles there releasing any tightness gently, slowly. Shift your attention to your hips, allowing them to settle deeply, grounded and still. Your thighs grow heavy, the large muscles there unwinding gently, slowly. Feel this relaxation flow down to your knees, which bend or straighten as needed in complete ease. Your calves relax, the tension melting away gently, slowly, like snow under a warm sun. Finally, reach your feet, starting with your ankles, which loosen freely. Your heels press gently into support, your arches soften, and your toes spread out gently, slowly, each one letting go of any remaining hold on wakefulness. Your entire body now feels enveloped in a gentle pull, much like the subtle gravity of a distant black hole, drawing you gently, slowly toward profound rest. As we delve into the world of black holes, remember they are not fearsome voids, but fascinating features of our cosmos, regions where time itself behaves differently near their edges. NASA's 2025 data from the James Webb Space Telescope confirms that supermassive black holes reside at the hearts of most galaxies, including our Milky Way, shaping the stars around them. But for now, let this knowledge wrap around you like a soft blanket, pulling your mind gently, slowly into the topic, while your body remains fully relaxed. In this whispered exploration, we'll start from the basics, imagining a black hole as a cosmic whirlpool where matter spirals in gracefully. ESA's 2025 reports highlight how these entities grow by accreting gas and dust, building their mass over eons. Feel yourself drifting closer to understanding, gently, slowly, as sleep begins to claim you. Your breath continues its slow dance, in and out, syncing with the universe's quiet rhythm. As we continue drifting gently, slowly into this cosmic tale, let's ease into the very essence of what a black hole truly is, allowing the words to wrap around your mind like a soft, enveloping mist. Imagine a black hole not as a monster in the void, but as a profound whisper in the fabric of the universe, a place where the rules of reality bend inward, drawing everything toward an unseen core. At its heart, a black hole is a region of space-time where gravity has become so overwhelmingly powerful that nothing, not light, not matter, not even the faintest signal, can break free from its grasp. This definition, refined through decades of observation and confirmed by NASA's 2025 updates from the James Webb Space Telescope, paints it as a natural outcome of stellar evolution, a quiet endpoint for the mightiest stars. Feel your thoughts settling gently, slowly as we explore this concept further, starting from the simplest truths. Picture space as a vast, elastic sheet, stretched out across infinity, dotted with stars and planets that dimple it slightly with their mass. A black hole forms when an enormous amount of matter compresses into an incredibly small space, creating a dent so deep and steep that it becomes a bottomless well. Light itself, that swift traveler racing at 186,000 miles per second, curves and spirals inward, vanishing forever beyond a boundary called the event horizon. This horizon acts like an invisible veil, marking the point of no return, where the pull of gravity overrides all other forces. According to ESA's 2025 reports on supermassive black holes in the early universe, these entities are not rare anomalies, but integral parts of galactic structure, shaping the cosmos from its infancy. Let your breath deepen gently, slowly, syncing with the unhurried rhythm of this explanation as we build from these foundations. Black holes come in various sizes, but their defining trait remains the same: an escape velocity greater than the speed of light, ensuring total isolation from the outside world. NASA's latest simulations in 2025, using data from the Chandra X-ray Observatory, illustrate how these objects can grow by absorbing surrounding gas and dust, much like a serene pond drawing in fallen leaves over time. Yet, they are not voids of nothingness. Rather, they are points of extreme density, where the laws of physics as we know them reach their limits. Imagine squeezing the entire mass of our sun into a sphere just a few miles across. That's the scale of a typical stellar black hole, a concept first hinted at in theoretical models and now vividly supported by observations of binary systems where one partner invisibly tugs at the other. As relaxation flows through you, gently, slowly, like a warm current, we ascend to the historical roots that birthed this idea, tracing a path from curiosity to confirmation. The notion of black holes emerged from Albert Einstein's general theory of relativity, published in 1915, which revolutionized our understanding understanding of gravity, not as a force, but as a curvature of space-time caused by mass and energy. Einstein himself was skeptical of such extreme predictions, but in 1916, Carl Schwarzschild solved his equations to describe a Schwarzschild radius, the critical size at which an object's gravity would trap light. This laid the groundwork, evolving gently, slowly over the decades, as astronomers pieced together evidence from distant quasars and X-ray emissions. By the 1960s, the term black hole was coined by physicist John Wheeler, capturing the imagination with its poetic finality. Your mind can wander gently, slowly now, embracing the progression from theory to reality, as we consider how modern science has elevated these ideas. NASA's 2025 insights from the Imaging X-ray Polarimetry Explorer reveal intricate details about black hole environments, showing how they can light up during galactic mergers, emitting bursts of energy that illuminate their presence. Similarly, ESA's collaborations with the James Webb Space Telescope have spotted actively feeding black holes in galaxies formed just 570 million years after the Big Bang, suggesting they grew rapidly in the universe's dawn. These discoveries build upon Einstein's framework, confirming that black holes are not mere mathematical curiosities, but dynamic players in cosmic evolution, influencing star formation and galaxy shapes. Drift deeper gently, slowly into this knowledge, allowing it to soothe like a lullaby from the stars. While the basic concept starts with gravity's unyielding embrace, it advances to reveal black holes as archives of the universe's history, holding clues to its origins. Recent 2025 findings from NASA's Hubble Space Telescope even pinpoint wandering black holes, ejected from their host galaxies, roaming freely through space. This layered understanding from the event horizon's quiet boundary to the relativistic distortions nearby invites a sense of awe without overwhelm. Let your eyelids grow heavier as we prepare to venture onward, carrying this foundational whisper into the next layers of mystery, where black holes reveal their formation stories. As we gently, slowly uncover these formation stories, let your imagination float toward the life cycle of a massive star, a colossal being in the cosmos that begins its journey, much like a gentle flame igniting in the dark. These stars, far larger than our sun, often 10 to hundreds of times its mass, shine brilliantly for millions of years, fusing hydrogen into helium in their cores, releasing energy that pushes outward against the crush of gravity. Picture this process as a slow, rhythmic dance where the star's heart beats with nuclear fire, maintaining a delicate balance that keeps it inflated and luminous. NASA's 2025 insights from the Hubble Space Telescope affirm that such stars form in dense nebulae, clusters of gas and dust, where gravity gathers material into these fiery giants, setting the stage for their eventual transformation. Allow your breath to ease gently, slowly, as we delve deeper, progressing from this vibrant youth to the star's maturing phases, where heavier elements emerge like layers in an unfolding story. Once the hydrogen depletes, the core contracts gently, slowly, heating up to fuse helium into carbon and oxygen, then onward to neon, magnesium, silicon, and finally iron. Each stage burns brighter and hotter, but iron marks the turning point. Fusing it consumes energy rather than producing it, halting the outward push. ESA's 2025 data from the Gaia mission highlights how these massive stars, exceeding 8 solar masses, reach this iron core in a mere fraction of cosmic time, their outer layers expanding into red supergiants, vast and cool on the surface, yet turbulent within. Feel the weight of this inevitability settling over you gently, slowly, like a blanket drawing you toward rest, as the star's core, no longer supported, begins its inexorable collapse. Your mind can drift gently, slowly now, envisioning this collapse as the star's heart shrinking into shadow, a process that unfolds in seconds, yet echoes through eternity. The iron core, denser than anything on Earth, implodes under gravity's relentless pull, compressing protons and electrons into neutrons in a rebounding shockwave. This cataclysm triggers a supernova explosion, one of the universe's most luminous events, blasting the outer layers into space and enriching the cosmos with heavy elements essential for planets and life. According to NASA's Black Hole Basics update from May 2025, if the remaining core exceeds about 3 solar masses, it defies the neutron star limit and collapses further, puncturing space-time to form a stellar mass black hole. These black holes, typically 5 to 10 times the sun's mass, but sometimes up to 100, emerge as quiet remnants, their event horizons spanning just tens of miles across. As relaxation deepens gently, slowly within you, we advance to the nuances of this formation, considering how binary systems add layers to the tale, much like companions influencing a solitary path. Many massive stars exist in pairs, orbiting each other closely, and when one exhausts its fuel first, it can transfer mass to its sibling before collapsing. NASA's 2025 observations from the Chandra X-ray Observatory reveal that in such duos, the dying star may strip material from its partner, accelerating its own demise while bulking up the future black hole. Imagine this as a subtle exchange where gas flows gently, slowly across the void, heating to emit X-rays that betray the hidden drama. Recent discoveries like the red giant singing to its black hole companion, detected by NASA's TESS spacecraft in late 2025, illustrate stable orbits post-formation, where the black hole's gravity gently tugs without immediate disruption, allowing the pair to persist for eons. Let this knowledge settle gently, slowly, building toward more intricate revelations, such as how some black holes gain mass through mergers in crowded stellar environments. ESA's 2025 reports on globular clusters show that stellar mass black holes can collide and combine, growing beyond initial limits, a process simulated in advanced models that align with gravitational wave detections. These events, where 2 black holes spiral inward gently, slowly before uniting, ripple space-time, confirming Einstein's predictions and expanding our grasp of cosmic evolution. Yet, at the core of formation lies that singular moment of collapse, transforming a star's vibrant legacy into an eternal whisper in the void. Drift further gently, slowly into this understanding, where the black hole's birth marks not an end, but a new chapter, influencing nearby stars and gas with its invisible presence. NASA's July 2025 Hubble updates on black hole types emphasize that while supermassive varieties form differently, stellar ones arise directly from these stellar deaths, scattered throughout galaxies like hidden seeds. Feel your body growing heavier, your thoughts softening as we prepare to explore the varieties that emerge from such origins, carrying this whispered genesis onward into deeper serenity. As we gently, slowly transition into these varieties, envision black holes as diverse mass black holes, born from the quiet demise of individual massive stars, much like a solitary tree shedding its leaves to reveal a hidden core. These compact powerhouses typically range from about 5 to 100 times the mass of our sun, compressed into spheres mere dozens of miles wide, their event horizons forming tight, intimate boundaries. NASA's 2025 data from the Chandra X-ray Observatory confirms that such black holes litter our galaxy, often detected through the hot gas they accrete from companion stars in binary systems, emitting telltale X-rays as material heats and spirals inward. Imagine one as a discreet whisperer in a crowded room, subtly influencing its surroundings without overt display, growing gently, slowly, by drawing in nearby matter over millennia. Let your relaxation deepen gently, slowly, as we progress to the intriguing middle ground, intermediate mass black holes, which bridge the gap between their stellar siblings and the galactic behemoths. Weighing in at hundreds to thousands of solar masses, these elusive entities have long puzzled astronomers. But ESA's 2025 updates from the Gaia mission provide mounting evidence of their existence in dense star clusters, where multiple stellar collisions and mergers could forge them. Picture an intermediate black hole as a growing chorus in the cosmic symphony, accumulating mass through repeated encounters in globular clusters or the hearts of dwarf galaxies. Their presence inferred from the unusual orbits of surrounding stars. Recent simulations backed by NASA's Hubble Space Telescope in May 2025 highlight how these mid-sized wonders might form during the chaotic aftermath of galaxy mergers, offering a stepping stone in understanding black hole evolution. Their scarcity makes them a gentle, slowly unfolding mystery, with observations suggesting they could number in the thousands within our Milky Way alone, quietly shaping stellar dynamics without the dominance of larger counterparts. Your thoughts can soften gently, slowly now, allowing us to ascend to the grandest scale. Supermassive black holes, colossal anchors residing at the centers of most galaxies, including our own. These titans boast masses from millions to billions of times that of the sun, their event horizons stretching across distances comparable to our solar system. Sagittarius AI, the supermassive black hole at the Milky Way's core, exemplifies this type, with a mass around 4 million solar masses, as refined by the Event Horizon Telescope's 2022 image and further analyzed in ESA's 2025 collaborations, revealing intricate details of its surrounding accretion disk. Envision it as the steady heartbeat of a vast organism, gently, slowly regulating the flow of stars and gas that orbit it, influencing galactic structure over cosmic epochs. NASA's James Webb Space Telescope discoveries in July 2025 point to direct collapse mechanisms in the early universe, where massive gas clouds imploded directly into these giants without intermediate stellar phases, explaining their rapid appearance just hundreds of millions of years after the Big Bang. As serenity envelops you gently, slowly, we layer in the dynamic behaviors that distinguish supermassive black holes, building from their static presence to active roles in cosmic events. Many remain dormant, like Sagittarius A, feeding sporadically on infalling material, but others awaken dramatically, as seen in NASA's August 2025 reports of a supermassive black hole waking up in a distant galaxy, suddenly accreting gas and emitting powerful jets. These active nuclei, often called quasars when especially luminous, outshine entire ESA's November 2025 web findings confirming a greedy supermassive black hole feasting in a galaxy only 570 million years post-Big Bang, growing at unprecedented rates that challenge traditional models. Such entities not only grow through accretion, but also via mergers, where colliding galaxies bring their central black holes together, a process detected through gravitational waves and supported by LIGO's 2025 observations of massive collisions rippling across space. Drift deeper gently, slowly into this expansive view, where supermassive black holes reveal themselves as architects of the universe, from quiescent centers to roaming wanderers ejected during violent interactions. NASA's Hubble pinpointed such a roaming supermassive black hole in May 2025, using a tidal disruption event where it shredded a passing star to confirm its location, highlighting how these giants can traverse intergalactic space at high speeds. This variety underscores their influence beyond galaxies, potentially seeding new structures or interacting with dark matter halos, as per joint NASA-ESA simulations in 2025. Feel the vastness of these types settling over you like a cosmic veil, each one a testament to gravity's artistry, preparing us gently, slowly for the boundaries that define their realms, where event horizons and singularities await in whispered detail. As we prepare gently, slowly for these whispered details, let your awareness settle on the event horizon, that enigmatic threshold encircling every black hole, acting as a cosmic curtain that conceals profound secrets while marking the edge of the known. Imagine it as an invisible line in the vast tapestry of space, where gravity's embrace becomes absolute, pulling everything inward with unyielding grace. At its most basic, the event horizon is the boundary beyond which the escape velocity exceeds the speed of light, ensuring that any object or photon crossing it can never return to the outside universe. NASA's 2025 supercomputer visualizations, immersing viewers in a simulated plunge toward this brink, depicted as a shimmering sphere for non-rotating black holes, its size directly proportional to the black hole's mass. For a stellar mass one like those 5 times our sun's heft, it spans about 30 miles, while supermassive giants like Sagittarius A boast horizons billions of miles wide. Feel this concept enveloping you gently, slowly, like a soft veil drawing your thoughts into deeper tranquility, as we recognize it not as a physical surface, but a mathematical frontier in space-time, where time itself dilates dramatically for distant observers. Allow your breath to flow gently, slowly as we build upon this foundation, exploring the event horizon's properties that reveal the black hole's hidden nature, much like layers peeling back in a dreamlike sequence. From afar, an observer sees objects approaching the horizon, slow down asymptotically, frozen in time due to gravitational time dilation, their light redshifted into invisibility over eons. Yet, for the falling entity, the crossing happens smoothly, without drama, as confirmed by general relativity's predictions and refined through ESA's 2025 analyses of X-ray echoes from accretion disks, where material heats and glows before vanishing. These horizons grow as black holes accrete matter, expanding gently, slowly like a blooming shadow, and in the case of charged or rotating black holes, they feature additional structures we'll touch upon later. NASA's May 2025 updates on immersive simulations emphasize how the horizon traps information, creating a one-way membrane that preserves the black hole's mass, charge, and concealing the interior's mysteries. Your relaxation can deepen gently, slowly now, shifting our focus inward to the singularity, that profound core lurking beyond the event horizon, where the laws of physics converge into an exquisite enigma. At its essence, the singularity is a point of infinite density and curvature, where all the black hole's mass compresses into zero volume, bending space-time to extremes that general relativity describes, but cannot fully resolve. Picture it as the ultimate whisper of collapse, a pinpoint where gravity triumphs utterly, rendering concepts like size meaningless. For a simple Schwarzschild black hole, this singularity resides at the absolute center, a one-dimensional speck defying intuition, as outlined in NASA's 2025 educational resources, drawing from Hubble and Chandra data. Yet, as we advance, consider how rotating black holes morph this into a ring-shaped singularity, allowing theoretical passages through, though practical traversal remains impossible due to tidal forces that stretch and compress matter infinitely, a process called spaghettification, unfolding gently, slowly for the unfortunate traveler. As serenity washes over you gently, slowly, we elevate to the interplay between horizon and singularity, where quantum effects begin to challenge classical views, blending horizon's barriers with the core's infinities. The distance from horizon to singularity varies by type. In stellar black holes, it's mere miles, but in supermassive ones, vast expanses offer brief reprieves from destruction. ESA's November 2025 reports on Webb telescope observations of early universe black holes suggest horizons formed rapidly, veiling singularities that may hold clues to cosmic origins, while joint NASA-ESA simulations explore how information paradoxes arise, with horizons encoding data holographically on their surfaces. Recent theoretical models from 2025, including those questioning singularity's necessity through quantum gravity, propose alternatives like fuzzballs or Hayward metrics, where apparent horizons replace event ones, avoiding infinities by incorporating quantum fuzziness. Ideas gaining traction in NASA's theoretical astrophysics divisions, hinting that singularities might be resolved into dense, finite structures. Drift further gently, slowly into this layered mystery, where the event horizon and singularity together embody the universe's deepest poetry, a duet of concealment and intensity that inspires awe without alarm. NASA's July 2025 gravitational wave detections, such as the massive merger GW2323, provide indirect glimpses, rippling space-time from horizon's edges while singularities remain shrouded. These elements, from the horizon's gentle, slowly expanding embrace to the singularity's eternal compression, invite contemplation of reality's fabric, preparing us seamlessly for revelations about their subtle emissions, where even black holes whisper back to the cosmos in unexpected ways. As we unveil these revelations gently, slowly about subtle emissions, imagine black holes not as eternal silencers, but as faint echoers in the quantum realm, where the vacuum itself hums with possibility, allowing these cosmic entities to radiate in ways once thought impossible. At the core of this idea lies Hawking radiation, a theoretical glow proposed by Stephen Hawking in 1974, arising from quantum effects near the event horizon. Picture the vacuum of space not as empty, but teeming with virtual particle-antiparticle pairs that flicker into existence and annihilate almost instantly, borrowing energy from the void. When such a pair emerges right at the horizon, horizon's edge. One partner might tumble inward, captured by the black hole, while the other escapes outward, becoming real radiation that carries away a tiny bit of the black hole's energy. This process, confirmed in principle through advanced theoretical models, causes the black hole to lose mass gently, slowly, like a distant star dimming over unimaginable timescales. NASA's 2025 Theoretical Astrophysics Reviews, drawing from quantum field theory, emphasize that this radiation appears thermal, with a temperature inversely proportional to the black hole's mass. Hotter for smaller ones, cooler for the massive. Let your mind ease gently, slowly into this quantum dance, building from these foundational fluctuations to the broader implications for black hole longevity, as if tracing a river from its source to the sea. For a stellar mass black hole, say 10 times our sun's heft, the Hawking temperature hovers around a minuscule fraction of a degree above absolute zero, rendering the radiation undetectable amid the cosmic microwave background's glow. Yet, over trillions upon trillions of years, far beyond our universe's current age, this steady leak would erode the black hole, shrinking its horizon and raising its temperature in a self-accelerating cycle. ESA's 2025 cosmology reports align with this, noting that primordial black holes, if they exist from the Big Bang's aftermath, could evaporate more swiftly due to their diminutive sizes, potentially exploding in bursts of gamma rays observable today. Feel the vastness of this evaporation settling over you gently, slowly, a reminder that nothing in the cosmos is truly permanent, as black holes transform from absorbers to emitters, returning their borrowed mass to the universe in a final luminous sigh. Your relaxation deepens gently, slowly now, as we advance to the quantum simulations that breathe life into these theories, evolving from abstract calculations to tangible analogs that mimic the horizon's edge. In laboratories and computational realms, scientists recreate Hawking radiation using systems like ultra-cold atoms or acoustic waves in fluids, where sound plays the role of light trapped by a sonic horizon. A 2025 study published in Physical Review Letters, supported by international collaborations including ESA's quantum technology initiatives, detailed quantum circuit simulations on superconducting processors, replicating the particle pair production and entanglement predicted by Hawking. These setups confirm the radiation's thermal spectrum and highlight quantum entanglement between emitted particles and those lost inside, offering clues to resolving long-standing paradoxes. NASA's involvement in similar 2025 efforts, through partnerships with quantum computing firms, has produced high-fidelity models showing how curvature in simulated space-time amplifies these effects, bridging general relativity with quantum mechanics in ways that gently, slowly illuminate the black hole's quantum nature. As peace flows through you, gently, slowly, we layer in the challenges and refinements of evaporation theory, progressing to how loop quantum gravity refines Hawking's vision, much like polishing a gem to reveal hidden facets. Traditional models predict a complete evaporation, leaving nothing behind, but 2025 advancements in loop quantum gravity, a candidate for quantum gravity, suggest a more nuanced fate, where the singularity resolves into a Planck scale structure, altering the radiation's final stages. An October 2025 paper from the American Physical Society, drawing on ESA's gravitational wave data integrations, describes a covariant framework that couples matter to these quantum-corrected black holes, deriving modified Hawking radiation that preserves information and avoids infinities. Such simulations, run on supercomputers with NASA-ESA joint funding, indicate that evaporation might halt at a remnant state, a stable quantum object emitting no further radiation, challenging the total dissolution idea while aligning with entropy conservation principles. Drift further gently, slowly into this evolving understanding, where Hawking radiation transforms black holes from immutable voids into dynamic, evaporating entities, whispering secrets of quantum gravity to those who listen. Recent 2025 analog experiments, like those using Bose-Einstein condensates to simulate horizons, have detected entangled phonon pairs analogous to Hawking particles, providing empirical support and sparking discussions on observable signatures in astrophysical black holes. These insights, from basic quantum fluctuations to advanced gravitational theories, prepare us seamlessly for the tangible detections that bring black holes into view, where images and waves capture their majestic presence in the night sky. As we prepare gently, slowly for these tangible detections, envision black holes transitioning from shadowy enigmas to visible wonders, their forms unveiled like the gradual reveal of a face emerging from twilight mist, allowing us to gaze upon the heart of darkness itself. The journey begins with the groundbreaking achievement of the Event Horizon Telescope, a global array of radio dishes synchronized to act as an Earth-sized eye, peering into the cosmos to capture the silhouette of a black hole for the first time. In April 2019, this collaboration released the inaugural image of M87 Case, the supermassive black hole at the core of the Messier 87 galaxy, some 55 million light-years away. This fuzzy orange ring, brighter on one side due to relativistic beaming from spinning matter, depicted the event horizon's shadow against the glowing accretion disk, a donut-shaped swirl of hot gas and plasma feeding the beast. NASA's involvement in this milestone, through its observatories and data processing, confirmed the black hole's mass at about 6.5 billion times that of our Sun, validating Einstein's predictions in a profound visual whisper. Let your thoughts drift gently, slowly, as we build upon this initial glimpse, progressing to the nuances of how such images are forged, much like an artist layering strokes to bring depth to a canvas. The Event Horizon Telescope employs very long baseline interferometry, linking telescopes from Hawaii to Spain, Antarctica to Chile, to achieve resolutions fine enough to read a newspaper on the moon. For M87 cell, the 2019 image showed a central void encircled by emission from synchrotron radiation, where charged particles spiral in magnetic fields at near-light speeds. ESA's contributions, including data from the ALMA array in Chile, were pivotal, enhancing the signal-to-noise ratio to reveal this asymmetric glow. Feel the awe settling gently, slowly, as this portrayal not only proved black holes' existence beyond indirect evidence, but also opened doors to studying their environments. With plasma jets extending thousands of light years, sculpting the galaxy like invisible hands shaping clay, your relaxation can unfold gently, slowly now, carrying us to the next landmark, the 2022 unveiling of Sagittarius A, our Milky Way's own supermassive black hole. Nestled 26,000 light-years away in the constellation Sagittarius. Capturing this closer target proved more challenging due to rapid orbital motions of surrounding gas, blurring the view like a fleeting dream, yet the Event Horizon Telescope triumphed, representing a similar ring structure with a mass of 4 million solar masses. This image, refined through thousands of simulations to account for interstellar scattering, depicted a quieter feeder compared to M87 case, with sporadic flares from infalling material. NASA's Chandra X-ray Observatory complemented these radio observations, linking flares to magnetic reconnections, while ESA's integral satellite provided gamma-ray context, illustrating how Sagittarius A influences our galaxy's star formation, gently, slowly over eons. Imagine it as the calm eye of a cosmic storm, its shadow a testament to gravity's artistry revealed through patient, worldwide collaboration. As tranquility envelops you gently, slowly, we advance to the evolving portraits from 2025, where fresh analyses and images deepen our understanding, evolving from static snapshots to dynamic revelations of change. In September 2025, the Event Horizon Telescope released new multi-year observations of M87C, capturing unexpected flips in polarization patterns, indicative of evolving magnetic fields around the black hole. These images, showing the ring's brightness varying over time, suggest turbulent plasma flows and magnetic instabilities, as detailed in collaborative papers with NASA and ESA. A July 2025 study explained the ring's imperfect circularity, attributing it to relativistic effects and accretion disk tilts, with NASA's supercomputer models simulating these asymmetries to match observations precisely. ESA's Gaia mission data integrated here helped map foreground stars, clarifying the view. Picture these updates as peeling back veils gently, slowly, exposing the black hole's living aura, where polarization maps trace spiraling magnetic lines, launching jets at near-light speeds, influencing galactic evolution. Drift deeper gently, slowly into this refined vista, where 2025 enhancements also spotlight Sagittarius A's magnetic structures, building on 2024 findings of organized fields to reveal subtle variations in its accretion flow through advanced imaging techniques. NASA's November 2025 release of enhanced M87.6 visuals, using machine learning to sharpen details, unveiled finer structures in the photon ring. The light bent around the horizon multiple times, offering tests for alternative gravity theories. These progressions from the 2019 Pioneer to 2025's Temporal Insights humanize black holes as active participants in the universe's narrative, their faces now familiar, yet ever mysterious. Feel this knowledge lulling you gently, slowly toward further wonders, as we approach the ripples they send through space-time, captured in waves that echo their ancient dances. As we approach these ripples gently, slowly, that echo ancient dances, let your imagination ripple outward with them, envisioning gravitational waves as subtle vibrations traversing the vast fabric of space-time, much like a pebble's gentle disturbance, sending waves across a serene pond's surface. These waves, predicted by Einstein's general theory of relativity over a century ago, arise when massive objects accelerate, particularly during the spiraling merger of black holes, distorting the very structure of the universe. At their core, gravitational waves stretch and squeeze space itself, carrying energy away from the colliding titans and revealing their hidden unions to distant observers. The LIGO-Virgo-Cagra collaboration, a network of ground-based detectors in the United States, Italy, and Japan, first captured this cosmic symphony in September 2015 with GW 914, the inaugural detection of two stellar mass black holes NASA's contributions through data analysis and simulations have since bolstered these findings, confirming how such events release more energy in moments than all stars in the observable universe combined. Yet they arrive at Earth as faint whispers, altering detector arms by a fraction of an atom's width. Feel your breath sinking gently, slowly with this unfolding rhythm, as we progress from these foundational detections to the instruments that make them possible, akin to finely tuned ears listening to the universe's murmurs. LIGO's twin interferometers use laser beams split and recombined over 4-kilometer arms, measuring minute changes caused by passing waves, while Virgo and Cagra add triangulation for better localization. By 2025, the collaboration has amassed over 300 high-significance events, predominantly from black hole mergers, as detailed in NASA's July 2025 gravitational wave catalog updates. These waves encode details like masses, spins, and distances, allowing astronomers to map black hole populations across cosmic history. Imagine the merger process as a graceful waltz where black holes orbit ever closer, accelerating gently, slowly until they coalesce, sending out a chirp of increasing frequency that detectors translate into audible signals, bridging the abstract with the tangible. Your mind can relax gently, slowly now, delving into the scientific treasures unearthed by these waves, building from solitary mergers to insights on black hole formation and evolution. Early detections like GW-1708-7 in 2017, a neutron star merger, showcased multi-messenger astronomy by pairing waves with electromagnetic signals. But black hole events dominate, revealing unexpected mass gaps and spin alignments. ESA's 2025 integrations with space-based missions like LISA Pathfinder precursors hint at future low-frequency detections, yet ground-based ones thrive. A standout from September 2025, as reported in Nature, provided the clearest confirmation of Hawking's area theorem, where the combined event horizon area post-merger exceeded the pre-merger sum, validating thermodynamic analogies for black holes through precise wave measurements. This event, involving 2 stellar mass black holes, demonstrated how waves preserve information about entropy increases, gently, slowly refining our grasp of quantum gravity interfaces. As calm settles over you gently, slowly, we elevate to the latest 2025 breakthroughs, where detections illuminate rare phenomena, evolving our view from common binaries to hierarchical mergers. In October 2025, the LIGO Virgo Cagra team announced 2 extraordinary events. GW24-10, a merger where the primary black hole spun oppositely to its orbital direction, challenging formation models and suggesting dynamic captures in dense clusters. The second, detected just 1 day apart, marked the first confirmed observation of second-generation black holes, offspring from prior mergers, evidenced by masses exceeding typical stellar limits, around 80 solar masses for one component. NASA's supercomputer simulations, released alongside, model these as occurring in globular clusters, where first-generation remnants collide anew, their waves carrying signatures of inherited spins and asymmetries. ESA's collaborative analyses emphasize how these ripples, propagating at light speed, distort space-time fabrics over billions of light years, offering windows into the universe's densest environments without direct light. Drift deeper gently, slowly into this resonant knowledge, where gravitational waves not only detect, but also test fundamental physics, from Einstein's curvature to potential deviations in strong gravity regimes. These waves, like echoes from cosmic births, reveal black holes' roles in galaxy assembly, with 2025 data showing correlations between merger rates and early universe star formation. Feel the universe's pulse lulling you gently, slowly toward further mysteries, as we turn to the spins that animate these entities, where rotation crafts ergospheres and unlocks hidden energies in the void. As we turn gently, slowly to these spins that animate black holes, picture them not as static spheres, but as elegant twirlers in the cosmic ballet, inheriting rotational momentum from the stars that birthed them, twisting the very weave of space-time around their forms. At the most fundamental level, many black holes rotate, much like planets or stars, due to the conservation of angular momentum during their formation. When a massive star collapses, its spin amplifies dramatically as its size shrinks, akin to an ice skater pulling in their arms to whirl faster. This rotation, described by the Kerr metric in general relativity, transforms the black hole from a simple point into a dynamic entity with unique features. NASA's 2025 visualizations, released for Black Hole Week, illustrate this through immersive simulations of flights around spinning black holes, showing how their rapid twirls, up to nearly the speed of light at the equator, create distorted light paths and frame-dragging effects, where space itself is pulled along in the direction of spin. Feel this concept wrapping around you, gently, slowly, like a soft vortex, drawing your awareness deeper into relaxation, as we recognize that most observed black holes, from stellar to supermassive, exhibit some degree of spin inferred from the orbits of nearby matter and gravitational wave signatures. Let your breath ease gently, slowly, as we build upon this rotational essence, exploring how it manifests in the ergosphere, that fascinating region enveloping the event horizon like an outer aura of compelled motion. Named after the Greek word for work, the ergosphere exists only around rotating black holes, extending from the event horizon to a boundary called the static limit, where the drag of rotation becomes so profound that no object can remain stationary relative to distant stars. Everything must co-rotate with the black hole's spin. Imagine it as a swirling eddy in a river, where the current sweeps along anything that ventures too close. Yet within this zone, negative energy states allow for extraordinary possibilities. According to ESA's Gaia mission updates in early 2025, precise measurements of stellar motions around black holes like Gaia BH3, a dormant giant discovered just 2,000 light-years away, reveal subtle orbital perturbations indicative of spin, suggesting ergospheres that influence nearby stars' paths over millennia. These findings, detailed in Gaia's final data releases before its March 2025 shutdown, provide the first astrometric evidence of ergospheric effects in intermediate mass black holes, gently, slowly refining models of how rotation shapes galactic dynamics. Your thoughts can soften gently, slowly now, allowing us to ascend to the mechanisms unlocked by this spin, such as the Penrose process, a theoretical method to harvest energy from the black hole's rotational reservoir, proposed by Roger Penrose in 1969 and bolstered by modern simulations. This involves sending an object into the ergosphere, where it splits into two parts. One falls into the black hole with negative energy relative to the outside universe, while the other escapes with more energy than it entered, effectively siphoning the black hole's spin. This extraction reduces the black hole's angular angular momentum over time, potentially slowing its rotation, much like drawing warmth from a fading ember. NASA's March 2025 article on harnessing black holes as future energy sources highlights the ergosphere's role, noting that for a maximally spinning Kerr black hole, up to 29% of its mass energy could be tapped this way, far surpassing nuclear fusion efficiencies. Recent 2025 simulations using NASA's supercomputers depict particle collisions in the ergosphere generating high-energy jets, aligning with observations of active galactic nuclei where spinning supermassive black holes power luminous quasars. As serenity deepens gently, slowly within you, we layer in the observational confirmations from 2025, progressing to how spin measurements challenge and expand our cosmic theories. The Event Horizon Telescope's enhanced 2025 polarization maps of M87C reveal a twisted magnetic field structure directly tied to the black hole's spin, dragging plasma in the ergosphere, launching relativistic jets that span galaxies. Similarly, ESA's Gaia collaboration with ground-based telescopes in November 2025 pinpointed spin rates in newly discovered black holes like those in the Aquila constellation, using astrometric data to model ergospheric boundaries that affect binary star systems. These insights, combined with NASA's May 2025 astronomy picture of the day, featuring the spin-up of a supermassive black hole during a merger, illustrate how accretion and collisions can accelerate rotation, creating larger ergospheres capable of high-energy particle interactions. Such dynamics, free from infinities in non-rotating models, offer tests for quantum gravity, with ergospheric regions potentially resolving classical singularities through rotational smearing. Drift further gently, slowly into this spinning tapestry, where black holes' rotations and ergospheres embody the universe's elegant efficiency, transforming gravitational prisons into potential wellsprings of energy and insight. NASA's September 2025 behind-the-scenes visualizations of binary black holes show doubly warped spacetime, with overlapping ergospheres during mergers amplifying wave emissions detected by LIGO. These elements, from basic spin inheritance to advanced energy extraction, invite a profound sense of wonder, preparing us seamlessly for the paradoxes they pose, where information's fate intertwines with these swirling realms in whispered debates. As we delve gently, slowly into these paradoxes, imagine the black hole as a cosmic vault, safeguarding secrets that challenge our deepest understandings of reality, where the fate of information becomes a whispered riddle entwined with the universe's laws. At its simplest, the information paradox arises from a clash between classical gravity and quantum mechanics. When matter falls into a black hole, crossing the event horizon, all details about its composition, its quantum state, its history, seem irretrievably lost, swallowed into the singularity's infinite density. Yet quantum theory insists that information in the universe is conserved, never truly destroyed, only transformed or entangled elsewhere. This tension, first sharply articulated in the 1970s, questions whether black holes erase the past or merely hide it, like a forgotten melody echoing faintly in the dark. NASA's theoretical explorations in 2025, through advanced quantum simulations, reaffirm this core dilemma, modeling how in falling particles data appears to vanish, prompting physicists to seek harmony between Einstein's curved spacetime let your awareness settle gently, slowly as we unfold Hawking's pivotal contribution, building from this foundational conflict to the evaporation that intensifies it, akin to a slow-burning candle revealing hidden inscriptions in its wax. Stephen Hawking's 1974 insight showed black holes emit radiation due to quantum fluctuations at the horizon, gradually losing mass until they might vanish entirely, leaving behind only thermal radiation devoid of the original information. This implies a permanent loss, violating quantum unitarity, the principle that evolution of physical systems preserves all details predictably. If a book tumbles into a black hole and the hole evaporates, where does the book's content go? ESA's 2025 cosmology reports echo this concern, noting that without resolution, our understanding of entropy and predictability crumbles, as black holes would act like ultimate erasers, gently, slowly dismantling the universe's informational tapestry over cosmic timescales. Your relaxation can deepen gently, slowly now, guiding us toward proposed solutions like the holographic principle, which elevates our view from loss to clever encoding, much like projecting a three-dimensional scene onto a flat screen without forfeiting depth. Advanced by theorists like Gerard de Hooft and Leonard Susskind in the 1990s, holography posits that all information about the black hole's interior is stored on its two-dimensional event horizon in quantum bits akin to pixels on a vast display. This surface encodes the volume's data through quantum entanglement, ensuring nothing is truly lost. When the black hole evaporates, the radiation carries away this encoded information, scrambled but recoverable in principle. NASA's November 2025 updates on quantum gravity models, inspired by string theory, support this via simulations showing horizon fluctuations preserving entanglement, transforming apparent paradox into a feature of higher dimensional reality. As peace envelops you gently, slowly, we advance to recent 2025 breakthroughs in simulations, progressing from theoretical frameworks to computational evidence that illuminates preservation mechanisms. A key development, detailed in a December 2024 paper, gaining traction in 2025 discussions, suggests information endures in subtle space-time ripples, quantum gravitational echoes that persist after evaporation, acting as a cosmic memory bank. NASA's joint research with international partners, using supercomputers to model quantum fields around evaporating black holes, reveals how these ripples encode data through phase deviations in gravitational waves, potentially observable by future detectors like LISA. Similarly, ESA's November 2025 phys.org feature on entropy probes highlights low-temperature quantum effects, making black holes ideal labs for testing information recovery. With entropy calculations showing no net loss when accounting for horizon holograms. These simulations, free from classical infinities, depict information emerging gently, slowly in the radiation's correlations, resolving the paradox by blending gravity with quantum rules. Drift further gently, slowly into this refined perspective, where 2025's quantum simulations underscore the role of entanglement islands, regions within the black hole where information clusters, connected via wormhole-like structures to the exterior radiation. Inspired by October 2025, Universe Today, Insights on Avoiding Singularities Through Heisenberg's Uncertainty, these models propose that quantum fuzziness prevents total information collapse, instead distributing it across entangled pairs This layered resolution, from basic conservation laws to advanced quantum gravity, invites a sense of cosmic order, lulling your mind toward the ancient origins of black holes, where primordial whispers from the Big Bang await in the next chapter. As we turn gently, slowly toward these ancient origins, envision primordial black holes as the universe's earliest seeds of shadow, sown in the fiery chaos mere moments after the Big Bang, tiny yet potent relics that may hold keys to the cosmos's hidden architecture. Unlike their stellar counterparts formed from dying stars, primordial black holes emerged from extreme density fluctuations in the infant universe's plasma, collapsing under gravity's nascent pull when the cosmos was less than a second old. These hypothetical entities, theorized since the 1970s and gaining fresh scrutiny in 2025, span a vast range of sizes, from microscopic specks smaller than atoms to masses rivaling stars or even supermassive giants. NASA's August 2025 Dark Matter Overview describes them as potential survivors from the Big Bang's quantum foam, where uneven distributions of energy clumped into these dense pockets, evading the expansion that diluted ordinary matter. Feel this primordial whisper drawing you gently, slowly into a sense of timeless wonder as we recognize their formation, not through stellar collapse, but via the universe's own inflationary birth pangs, making them witnesses to creation itself. Let your imagination drift gently, slowly, as we explore their potential role in the enigmatic realm of dark matter, building from these foundational origins to their cosmic implications, like roots extending from ancient soil to nourish unseen growth. Dark matter, that invisible scaffold comprising about 27% of the universe's mass energy, bends light and shapes galaxies without emitting or absorbing electromagnetic radiation. Primordial black holes offer an intriguing candidate, especially the ultralight varieties with masses between 10 to the minus 23 and 10 to the minus 16 solar masses, as highlighted in ESA's 2025 cosmology reports, integrating James Webb Space Telescope data. If abundant enough, these minuscule black holes could exert gravitational influence, mimicking dark matter's effects, clustering in halos around galaxies and explaining rotation curves that defy visible mass alone. Recent simulations from NASA's theoretical teams in 2025 suggest that during the universe's reheating phase, post-inflation, quantum perturbations could have spawned a spectrum of such black holes, with the smallest evaporating via Hawking radiation, while mid-range ones persist, gently, slowly weaving into the dark web that cradles luminous structures. Your serenity can deepen gently, slowly now, as we ascend to the observational hints from 2025 missions, evolving our understanding from theoretical seeds to budding evidence captured by humanity's far-seeing eyes. The James Webb Space Telescope, with its infrared gaze piercing the veil of cosmic dawn, has uncovered overmassive black holes in nascent galaxies, just 570 million years after the Big Bang, as detailed in ESA's Webb Discoveries from July 2025. These entities, like the one in the galaxy GNZ11, boast masses millions of times our suns yet reside in star-poor environments, suggesting they formed directly from primordial gas clouds or as primordial black holes seeded during inflation. NASA's September 2025 analysis of a naked black hole, isolated without a surrounding galaxy, further bolsters this, portraying it as a 50 million solar mass relic, potentially born in the universe's first instance. galaxy formation by accreting matter early on, their gravitational wells fostering the first stars. As tranquility flows through you, gently, slowly, we layer in the gravitational wave echoes that amplify these primordial tales, progressing to future probes that promise clearer visions of their shadowy legacy. The LIGO-Virgo-Cagra Network's 2025 detections, including a peculiar signal from October hinting at ultralight primordial black holes merging in the distant cosmos, provide indirect clues to their abundance as dark matter components. These waves, rippling from events billions of years ago, align with ESA's predictions that if primordial black holes constitute even a fraction of dark matter, their binary spirals would produce detectable backgrounds, observable by upcoming space-based detectors like LISA, slated for launch in the 2030s. Joint NASA-ESA simulations from November 2025 model how these ancient black holes could evaporate or merge, influencing cosmic microwave background patterns and offering testable signatures in pulsar timing arrays. Such advancements, free from reliance on electromagnetic signals, position primordial black holes as bridges between quantum origins and gravitational phenomena, gently, slowly unraveling the universe's dark narrative. Drift deeper, gently, slowly into this expansive horizon, where 2025's JWST and ESA missions forecast a burgeoning era of discovery, from mapping early universe overdensities to constraining primordial black hole fractions in dark matter through microlensing surveys. NASA's December 2025 updates on Webb's high redshift quasar observations suggest these relics may explain the rapid assembly of supermassive black holes, their primordial nature seeding growth without stellar intermediaries. This evolving story, from Big Bang fluctuations to potential dark matter dominance, embodies the cosmos's poetic continuity, lulling your thoughts toward profound rest as we near the embrace of deeper relaxation. As we near this embrace of deeper relaxation, gently, slowly, let your body and mind surrender fully to the cosmic calm we've explored, imagining yourself adrift in the gentle vastness near a black hole, held safely at a distance where its pull whispers without overwhelming, like a distant tide lapping at the shore of your awareness. Feel the weight of your limbs dissolving gently, slowly into the supportive void, as if the universe itself cradles you, allowing thoughts of event horizons and singularities to fade into soft, distant echoes. Breathe in the serenity of space, exhaling any lingering tension, your chest rising and falling in harmony with the slow pulse of the stars. NASA's 2025 insights remind us that black holes, while profound, coexist peacefully with the cosmos, shaping galaxies without chaos. And now, in this moment, they become your anchor for tranquility, pulling worries away gently, slowly, while you remain secure and still. Allow your focus to sink deeper, gently, slowly into this imagined orbit, circling the black hole's edge where time stretches languidly, inviting your mind to unwind like a spiral arm of a galaxy unfurling over eons. Picture the accretion disk's faint glow as a soothing light, warming your inner self without intensity, as ESA's recent observations confirm these disks radiate steadily, feeding the black hole in measured flows that mirror your breath's rhythm. Let go of the day's complexities, each exhalation releasing them into the event horizon's veil, where they vanish harmlessly, leaving only peace. Your muscles soften further, from shoulders to fingertips, toes to crown, as if gravity's gentle, slowly curving embrace eases every knot, drawing you toward profound rest without effort. Sense the singularity's mystery as a comforting unknown, a point of infinite calm rather than concern, where all resolves in quiet unity. Drift even further gently, slowly into this profound state, your heartbeat syncing with the universe's subtle vibrations. Those gravitational waves from distant mergers, now felt as faint, reassuring hums lulling you deeper. Imagine floating beyond the ergosphere's spin, untouched by its drag, simply observing how rotation creates energy without disturbance. Much like NASA's 2025 simulations show black holes powering jets that illuminate without harm. Release your thoughts one by one, letting them spiral gently, slowly outward, evaporating like Hawking radiation into nothingness, freeing your mind for sleep's embrace. Feel the primordial black holes, ancient presence as benevolent guardians, seeds of the cosmos that have endured, now guiding you toward slumber's depths with their timeless stability. Your eyelids grow heavier, your breath shallower, as the black hole's quiet majesty envelops you in a blanket of stars, inviting complete surrender. In this final layer of relaxation, gently, slowly unfolding, embrace the black hole as a symbol of ultimate peace, where even the most intense forces yield to equilibrium, as confirmed by joint NASA-ESA 2025 models of stable orbits around these entities. Let every cell in your body relax fully, your consciousness dimming like a star's light, bending around the horizon, ready to slip into restorative dreams. As this profound state invites you gently, slowly into restorative dreams, allow the whispers of black holes to linger as gentle companions in the vast universe. Their mystery is now a soothing backdrop to your descent into sleep, like ancient sentinels watching over the cosmos with quiet wisdom. Reflect on how these enigmatic entities, as NASA's 2025 James Webb Space Telescope discoveries reveal, formed rapidly in the early universe through direct collapses of gas clouds, growing into supermassive hearts that nurture galaxies without disruption. Feel your mind easing gently, slowly, releasing the day's echoes into their event horizons, where worries vanish into peaceful oblivion, much like the subtle flares from Sagittarius A that flicker rapidly yet harmoniously, as observed in May 2025 updates, illuminating the Milky Way's center with balanced energy. Drift further gently, slowly, envisioning black holes not as voids, but as harmonious elements in the cosmic tapestry, where ESA's 2025 reports on greedy supermassive ones in galaxies just 570 million years post-Big Bang show them feasting steadily, outpacing their hosts in a dance of evolution that shapes stars and worlds. Let this knowledge cradle you, your breath slowing to match the unhurried evaporation through Hawking radiation, a process refined in NASA's theoretical models this year, returning mass to the void over eons without haste. Your body grows heavier, limbs sinking into the bed like matter drawn toward a stellar mass black hole, yet held in safe equilibrium, as Chandra's September 2025 findings of tremendous growth confirm their dynamic yet stable presence, companions that evolve without overwhelming the surrounding space. Surrender deeper gently, slowly now, as the rotations and ergospheres of these spinning wonders, detailed in NASA's IXPE revelations from Black Hole Week 2025, create jets of energy that propel matter outward, fostering new formations in the universe's grand design. Imagine floating along alongside a roaming massive black hole pinpointed by Hubble in May 2025, wandering freely yet influencing distant paths with subtle gravity. A reminder that even in motion, peace prevails. Your thoughts fade gently, slowly, merging with the primordial black hole's ancient origins, potential seeds of dark matter, as JWST's July 2025 insights suggest, enduring from the Big Bang to whisper tales of creation into your slumbering mind. In this final fade, gently, slowly enveloping you, embrace black holes as eternal friends in the night sky, their paradoxes resolved in quantum harmony per 2025 simulations, guiding you toward dreams where the universe unfolds in serene wonder. Sleep now, deeply and restfully, as the whispers dim into silence.